Now let's talk about gas problems with stoichiometry. So unfortunately, all of us, myself included, have gas problems right now, and hopefully we'll resolve them soon. The ideal gas law allows us to convert from the volume of the gas to moles, and then we can use the coefficients in the equation or the reaction as a mole ratio. And so that's what we've been doing some calculations with now is given pressure, volume, and temperature of a gas, convert to moles. And that's done using the ideal gas law. Okay. And stoichiometry means that you're going to use a balanced reaction to convert from moles of A or moles of one thing to moles of B, something else. And when you do this, you always use the conversion factor that is based on the mole-to-mole ratio. And the mole-to-mole ratios are constructed by using the coefficients from the balanced reaction. And I will abbreviate coefficients such, COEFF, coefficients of balanced reaction. And that's nothing new. We've been doing that since we worked with grams to moles and moles to moles. But what we're doing is we're developing a little flow chart here, and we're going to put in the problems that we're about to do with gases, and then we're going to reference some of the other problems we've already talked about in previous chapters. And then if you want to go from moles of whatever it is to pressure, volume, and temperature, again, you need the ideal gas law. A flow chart, a roadmap of what we're doing here. Okay, and this is for gases. If you start with gases and you end with gases. Now, for previous problems that we've solved, we've started with a solid or solids. And when you do that, you are typically given grams. Of some substance. And to get to moles, you use a conversion factor, and that conversion factor we call the molar mass. So it has units of grams per mole, and that allows us to change the units. And on the other side, we can do the same thing. We can use the molar mass to get to grams of B. And for solids. Okay, so, and these are all of the calculations we can do. And again, the bottleneck here, or the point that we always have to go through, is using a mole-to-mole ratio with coefficients of the balanced reaction. Now, there are two other phases that we've talked about in this class. Those are the liquid phase and the aqueous phase for solutions. Let's tackle aqueous next. And I'll just write AQ here. When you're dealing with the aqueous phase, to get mole information, you're typically given milliliters of solution, or a volume of solution, but I'll write milliliters. So some sort of aqueous solution. And you're also given a molarity. And it is the molarity that allows you to convert into moles. So two pieces of information here. And likewise, on the other end, you can get to milliliters on the other side. Using molarity, this time molarity of aqueous B solution. And so we've actually now, these are all of the calculations that we typically do in this course, called stoichiometry calculations. And you can start with a PVT of a gas, and be asked for grams of one of the products or grams of one of the other reactants. You can move through any system here. And so this summarizes all of the calculations that we've had to do so far. There's one type of calculation that we haven't done, and I want to add that. It doesn't come up that often, but but it is a useful conversion factor. That's for the liquid phase. And for a liquid phase, the most typical way that you're given information about a liquid is you will be given milliliters of liquid. And you know that you're given milliliters of a liquid when the phase or state is called liquid. And when it's a liquid, it's a pure liquid. And that's how you tell it from milliliters of an aqueous phase, where A is a solute. And to get from milliliters to moles, you actually need two steps. One, you need the density of the liquid, because density will be in grams per mole, and that will allow you, density will be in grams per milliliter, which will allow you to convert milliliters into grams. And then once you have grams, you need molar mass, because that allows you to convert grams into moles. And we'll do the same thing for our flow chart over here. And again, this last type of calculation with pure liquids doesn't occur that often, but it's worth noting in case it does. Grams per milliliter, and then molar mass. So this chart is a summary of all the stoichiometry calculations that we can do in this course. And how the information is given to you depends on what phase you're dealing with. And these are all the phases we typically deal with in this course. And then the other thing to point out is you always go through the mole-to-mole ratio and the coefficients of the balanced reaction. So let's see how that works. This question says, what volume of hydrogen is needed to make 35.7 grams of CH3OH, that's methanol, at a specific pressure and a specific temperature? So we have 35.7 grams of methanol, a product in this case. We have grams of methanol. We'll use the molar mass to get to moles of A. Then we'll use the coefficients in the balanced reaction to get from moles of A, which is methanol, to moles of B, which is hydrogen. And then we'll use the ideal gas law to get to pressure, volume, and temperature. And in fact, what we're looking for this time is volume of hydrogen. So that's a roadmap for this problem. And this is a really useful thing to have while you work basically a lot of problems for the rest of the semester. So let me show you what I mean. So we're going to start with grams of methanol, CH3OH. Ooh. So scribble that out. We have grams of methanol. We're going to use the molar mass of methanol. And the molar mass of methanol is going to be 12.01. We have plus 4 for hydrogens times 1.08 plus 16. 32.04. Like so. From there, we need a mole-to-mole ratio. For this one, we're going to put 1 mole of methanol on the bottom and 2 moles of hydrogen on top. This will get us moles, and this is where I'm going to solve and then plug into the ideal gas law. There are ways to use the picket fence or the railroad tracks to solve the ideal gas law right in the picket fence, but and you're free to use that, but I'm going to separate them. let's see, so 35.7 grams divided by 32.04 times 2. I get 2.23 moles of hydrogen. Then I have moles, I have temperature, and I have pressure. I have some unit conversion to do here. Let's do that first. There are 760 millimeters of mercury in 1 atmosphere. .971. Then PV equals nRT. Plug everything in. I was looking for my volume, but that's what we're solving for. Always helps to reread the question. I have my moles. I always write out my ideal gas constant, liter atmospheres per mole Kelvin. And in Kelvin, my temperature is 355. Now again, so take all the right-hand side, divide it by the left-hand side to solve for my volume of hydrogen gas. Let's see, where can I do this? There we go. Apologize if this is a little jumpy. 2.23 times 0.08206 times 355 divided by 0.971. I get 66.9 liters, and that's a fine answer. You can also write of H2 gas, since that's what it is. This one is a companion problem. And this one is a companion problem as well.